Welcome to another HYTALK webinar. It's a pleasure to have you joining us. So my name is Paul Marley. I'm Technical Training Manager from HYTALK in Australia. Presentation today is entitled Sources and Types of Contamination. Okay, so sources and types of contamination. So again, thank you for joining us. It's a pleasure to have you with us. Now, what I was thinking of doing here is addressing one of the questions that we have with regards to subjects for the webinars and for the podcast that we do. So ultimately, there's been more interest in filtration than any other subject. So that's good because, being HYTALK, we know a lot about filtration. So the way I thought we'd address this is with a series of webinars. So this is the first one. This is entry level. So sources and types of contaminants as a subject today, measuring industrial cleanliness, the standards and so on and how they're applied, and evaluating filter performance. So these are the important fundamentals that you need to understand before we can talk about filtration more properly. Building on from that, we're looking at the different types of products that are available, the differences between them and where they're used in the system and how they could be made more effective. Suction filtration, pressure filtration, return line filtration, boost filtration, offline filtration, and filter breathers. So this is a series of webinars just talking about those products to understand the options that are available to come up with an engineering solution that makes a lot of sense and gives you the results that you're looking for. And then towards the end of the season, if I can call it that, filter media selection, how to actually choose what media we need in the element to make the results happen that we want to see in our system. And then filter sizing calculations. How do we actually size up the correct solution? So basically, that is the plan. And the plan is that we're going to do a webinar every 2 weeks. And this will see us then to the end of the year. It'll be almost Christmas. And that'll be a good thing because if we're almost at Christmas 2020, then 2020 is nearly over. And everyone's really been enjoying 2020. But the intention is that by then, we've learned a lot more about the filtration. So again, today's topic is number 1, sources and types of contaminants. Okay, so oil, fluid, hydraulic fluid, lubrication fluid. These lubricants, the condition, the characteristics and the care of these lubricants is absolutely fundamental. And they're fundamental to the reliable, predictable and safe operation of industrial equipment. But there's sometimes quite a big disconnect. There's little cause for discussions on these subjects from the metal trade competencies. So as a trainer, I get involved in these competencies quite a lot. So MEM 18020 and MEM 18021 maintain hydraulic system components and maintain hydraulic systems. So maintain hydraulic systems is really talking about how we repair things. And so is maintain hydraulic system components, how we repair things. If you think about it, it should really be repair hydraulic system components because that's really what it's addressing. The maintenance of a system, you would agree, is to keeping the lubricant in good order because if it is in good order, the breakdown's reduced up to 70% less. So the sciences involved here are well understood, particularly by reliability engineers, but not very well understood by those general tradespeople. And that includes myself when I was a general tradesperson. So ultimately, the reason for that disconnect is that this subject occurs in that very interesting space in between engineering and science. And this is where the spark happens. And it's quite an exciting place to learn about, actually. So ultimately, we know that there is a very clear relationship between technical cleanliness and machine reliability. And there's a very clear relationship between machine reliability and profitability. So it stands to reason, of course, that that's a straight line. If we can keep our lubricants clean, we keep our machines running, we make money off those machines. All right, sources of contamination. Ultimately, when we're making a system, the system is basically going to be made through industrial processes. And these are all dirty processes. We're going to be machining, generating swarf, we're going to be cutting, grinding, welding, painting, potentially sandblasting. So very dirty processes. And ultimately what we're looking for is a very, very clean component. Okay, so how do we make sure that that clean component is clean? Well, we have to be aware of everything that we do being dirty. So a lot of the contaminants in the system can be introduced during the assembly of that system through tubes and pipes, hoses, welding, grinding, sanding, general machining, painting, as I said. So we're going to be cutting tube. There's a lot of swarf involved in that. It's absolutely critical that these large chunks of steel are going to be excluded from our system. And the same is true with hoses. Hydraulic hoses, it's quite amazing how solid they can be. They can be sometimes comprising of as much steel as a similar sized tube or pipe. So as we're going to be cutting this, we can't just think this is just an industrial rubber, because there's a lot of steel going to be released into this hose as we cut it as well. And also, particularly these larger spiral type assemblies, if they're going to be cut using a drop saw, which is like a grinding disc, then we also have abrasives from the grinding disc also going to be deposited within the hose. So it's absolutely critical that as we're assembling that system, as we're assembling that hose, we have to absolutely clear that out, because those contaminants are very damaging. Another place where we can get these contaminants from is during the filling of the system. It's obvious to people that are involved in the fluids and the lubricants that these are going to be clean, because we've bought a new oil, it should be clean. The funny thing about the hydraulic systems and the lubricating systems, but in particular, is that fluid, when it's brand new out of a drum, will usually be much dirtier than it is for the rest of its life, if the system's working the way it should. Basically, new industrial lubricants are too dirty to put into a hydraulic and lubricating system. So as we fill that system that we've cleaned, we can contaminate it again. So it's absolutely critical that we are filtering the system with new, fresh, clean oil. As a rule of thumb, it costs 10 times more to remove a contaminant from a system than it does to exclude it in the first place. Okay? That's why it's absolutely critical that we filter our oil before we put it in the system. We can damage a system by basically preparing it, making it, testing it clean, and then damage it by putting it into storage. So the way that we store these components, if they're not going to be used immediately, is absolutely critical to us. The photo I've got here is from a system that was put in storage, and it was put back in service in this condition. Now, of course, a lot of the contaminants are going to be created during operation. There's going to be abraded particles purely by wear occurring in the system. Contaminants lead to further contamination. There's different wear processes, byproducts of oxidation within the lubricant itself. So it's absolutely essential that these systems are cleaned continually. Cleaning them once at the start isn't enough. So the filtration process will be ongoing for the life of the machine to get the cleanliness levels that we need. And of course, once the system is in operation, the environment's actually going to be trying to get itself into the system as well. We're going to get ingress through the wipers and the seals. Sometimes if you think about it, even the act of changing a filter element is an opportunity for contaminating your system. If you have a tank breather that's damaged, or in a lot of cases loose, off, or even lost, of course the environment gets in there. We think of air as being clean because we can see through it, but compared to the cleanliness we need in these systems, if that system is breathing normal air, industrial air, it's filthy. Okay, so the contaminants are introduced during the manufacture, during the use, and from the environment of these systems. So that's the origins of where it comes from. Let's explore the types of contaminants. When we think of contamination, the first thing we think of naturally is, of course, solid contamination, the particles. Okay, the particles can be very many things. As I said, a very abrasive grinding disc material, rust particles, welding scale. These are very damaging because they're very hard. Okay, very damaging to a system. Other metals that are involved in the system are, of course, iron from castings, steel from steel components. Very many components are bronze. Many pumps use bronze and other low-friction materials in them. And aluminium, of course, is used in very many products, pumps and manifolds as well. These are damaging components to a system. Can be quite damaging as well, but, size for size, they don't pack as much punch as the ones on the left. And then we have fibers from cloths, cleaning rags and so on, rubber debris from seals and hoses, oxidation residue from oxidizing fluids, and resin-bonded fabric. That's an interesting one. I suppose that's a term I wouldn't have thought of myself, but many industrial bearings that are used in cylinders and so on are going to have a fabric base with a resin molding. And these are, of course, less harmful, but they're still solid contaminants. So it's still, as far as the particle counter is concerned, but basically we really need a very, very low number of these because most systems can't tolerate these solid contaminants. But not every contaminant is going to be as damaging as another one, of course. I've said the material of the contaminant is very important to us. Other things that make a difference to how much damage they do is the physical size of those solid particles. Of course, the larger they are, the more damage they can do. But larger particles sometimes don't get caught in between running clearances. So sometimes medium-sized particles are very damaging as well. The amount of particles in the fluid, okay? So basically, how much damage are they doing? Well, how much dirt loading have you got? Well, that clearly stands to reason. The more you have, the more damaging it's going to be. But the shape and form of those solid particles makes a difference as well. Something that's hard material in a jagged shape is, of course, going to do more tearing than a softer material that's in maybe the shape of a ball. So the shape and form of the solid contaminants, the machine duty cycle, how often that machine is it running 24 hours a day, or is it simply running for 5 minutes every week? Makes a very big difference to how much contaminant you can tolerate in that system. Pressure patterns in the machine cycle over time. Certainly a machine that works at a higher pressure is pushing the internal parts of this system together and closing the tolerance. So generally speaking, a system that works at a higher pressure has a higher cleanliness requirement because the oil film is being challenged by that pressure loading. So the pressure patterns and what the machine is actually doing makes a big difference to the effects of them. The flow velocity has an effect as well, because certainly with regards to erosive wear, a higher velocity in the fluid is going to cause more erosion. So a high velocity dirty fluid is more damage than a low velocity clean fluid. And finally, of course, the machine components and their sensitivity to contaminants. So how much contamination a system can tolerate depends a lot on the system itself. And some systems are going to be having much more need of cleanliness than others. So it all comes down to the clearances involved in the components. So basically, these sorts of things we need to look at the other end of the webinar when we're looking at how we choose the media. We can't ignore the physical size, of course. So this is from a HYTALK catalog from the USA. Ultimately, what this chart is showing is that the visibility limit is around about 50 microns, and that's for someone who's got perfect vision. So anything under that, you can't see, not by the naked eye. You're going to need probably a microscope to be able to see these contaminants. 50 microns is a massive size contaminant for these systems. If I said, what size filters do you get? What are you trying to exclude? I think I'd be fair in saying people say, well, 10 microns comes to mind. Okay, well, that's 1/5 of what you can see. So it's very real that you can hold up a sample of fluid and go, yeah, that's clean. If we only evaluate with these things, okay, we can't necessarily do that in these technologies. Okay, so that's the physical size of the contaminant. So that pretty much rounds up the discussion on solid contamination. I just want to address liquid contamination. Of course, the most damaging fluid that we can find in some of these systems is water. So I've just put that over there as very damaging. Water is a poor lubricant. Water excludes oil, so we get a loss of lubricating film. Water causes hydrogen embrittlement of steels, damages bearings and makes them harder, makes them more easily to fatigue. So water is very, very bad. We certainly want to keep it out of there. So to address that one, well, how much water can we tolerate? As little as possible. Water is very bad. Where does it come from? It comes from fluid to fluid heat exchangers. Certainly these things do corrode, and you'll get an exchange of water into your lubricating fluid, or of course lubricating fluid into your water, which could be bad for the environment. So for these reasons, these shell and tube heat exchangers are actually not good enough for HYTALK to make. But that's a very real source of water contamination. Another way it gets into a system is by the storage of the lubricants, particularly if they're stored outside. Having a drum vertical like this is just going to have rain basically collect on the top. And then what happens then is as the day progresses, the drum will heat up. The fluid in the drum will expand and push the oil level up, pushing air out. So then what happens is as the drum cools down, potentially overnight, it's going to draw in a low pressure, and that's going to draw water in potentially. So you can basically get water into a sealed drum. For that reason, storing drums vertically is a very bad idea. just as a rule of thumb, if you're storing drums outside, try and put them on their side whenever they can. And if you align the bungs horizontally, then you're not going to be exchanging any air out of that drum, and it tends to keep that lubricant drier. So just a tip, but you can see how these practices are going to make a very big difference. Okay, and I've just got one little thing here. Other fluids can be contaminants as well. Just got that across the spectrum, very damaging, and less harmful. It depends on how much mixing is occurring and what that other fluid is. For example, maybe an engine oil that's getting in there, because you sometimes have multiple components separated with just a shaft seal or something, and those seals could get damaged. Other ways fluid gets into the system is by people just going, yeah, it's all right, mate, it's just oil. I've asked a few guys once when I was on site, okay, I need to know what sort of oil you've got in your tank here. Mate, I'll just put engine oil in it. Okay, but it looks like it had hydraulic oil in there first. Yeah, oil's, mate, yeah, it's all right. Gaseous contamination. Basically, hydraulic fluids will naturally hold some air, and they can hold up to 9% by volume of air, actually. Now, the air isn't particularly damaging, but the air contains oxygen, and the oxygen was one of the reasons we have oxidation occurring. So pulling the air out of a system is something that really increases the life of a system. And HYTALK have some technologies to do that, but this webinar isn't on that one. So air is ultimately something that we can remove, and we don't want to have an aerated fluid. Where does the air get into the system? The most common place is a loose connection on the suction of a pump. And as we have a low pressure area in that point, it's not necessarily going to be pushing oil out, and we'll see it as a visible leak, but it could be drawing air into that system. So that is basically one of the places that we're going to get aeration. Aeration is bad in a hydraulic system because it causes sponginess, because air is compressible in an incompressible fluid. You then have a compressible movement. You lose controllability. If you lose controllability, you potentially lose the ability to be safe as well and reliable. So that's air. And I'll just put in here nitrogen. You could have also nitrogen in there as a gaseous contaminant, because on reflection, if you have a hydropneumatic accumulator and that loses its bladder, well, that nitrogen is going to go into the oil because it can't go into the atmosphere. So it'll go into the oil, and basically it'll bubble through the system and out of the breather eventually. But if you do have a gaseous contaminant in your system, it could be nitrogen on its way out of that system as well. Okay, so that pretty much rounds up what we were talking about today. I'd just like to point out that we are doing webinars and podcasts as well. Don't forget to register for our upcoming webinars. Thank you very much.